Research in air traffic control has been conducted at NASA Ames Research Center since the early 70s. A rudimentary simulation capability has evolved over the years into a sophisticated real-time simulation of the air traffic environment, allowing controllers to participate in simulation runs where advanced scheduling concepts and traffic management tools can be evaluated. The current simulation resides on a Sigma-9 computer with simulation displays driven by an Evans and Sutherland graphics system, interfaced to the Sigma via a Digital Equipment Corporation PDP-1145 mini-computer. Pseudopilots respond to controller clearances by entering appropriate commands on the keyboard of their associated terminals. The ATC simulation is first started by starting up the PDP-1145 mini-computer for the ENS graphics system, then the simulation computer with the pseudopilot stations sequentially brought online. The pseudo-aircraft are generated by the simulation computer and appear in the flight data table on the screen. The terminal area is Stapleton International Airport at Denver, Colorado. The route structure is designed to utilize the arrival procedures published in the Standard Terminal Arrival, STAR, Profile Descent Runway 817-2635 for Stapleton International to an ILS-26L final approach. No departure flights, winds, or navigation errors are simulated. Aircraft enter the extended terminal area at the feeder fixes, flying at cruise speed and altitudes. The total distance to be flown by high-performance jets is 150 nautical miles, and that flown by low-performance aircraft is 60 nautical miles. 2 air traffic controller positions are used. The arrival controller controls aircraft from all 5 feeder fixes and transfers traffic to the final controller at approximately 30 nautical miles from touchdown. Control procedures differ for 4D-equipped and unequipped aircraft. Controllers are instructed to monitor the progress of 4D-equipped aircraft after the time assignment has been established, and to override the automated scheduler only if necessary to ensure safe separation. Any 4D-equipped aircraft can also be controlled by conventional methods. Alternatively, a 4D-equipped aircraft can be taken off its 4D route and time schedule, given a waypoint to recapture a 4D route, and be given a revised landing time. Unequipped aircraft are considered to be navigating in the conventional manner via very high-frequency omnidirectional range procedures with altitude clearances, radar vectors, and speed control. As we look at the arrival controller display, each aircraft is shown by a triangular symbol. Next to it is the aircraft ID, type, altitude in hundreds of feet, and speed. The information in the flight data table is generated by the scheduler and speed advisory system. Time is in hours, minutes, and seconds. The first column is aircraft ID. The next column specifies aircraft type, which includes weight category, S for small, H for heavy, and blank for large, 4 for 4D equipped, and U for unequipped. The third column designates the assigned route, KN for Kian, BK for Draco, BY for Bison, KO for Kiowa, and CS for Colorado Springs. The fourth column, schedule time of arrival, is runway touchdown time in minutes and seconds. For example, Romeo 1 is scheduled for touchdown at 13:41:10. The fifth column shows the expected delay at touchdown in seconds. Early arrivals are indicated by a negative value and late arrivals by a positive value, and a 0 value means on time. All 4D equipped aircraft depart from the feeder fix at the scheduled departure time and can meet time schedules within plus or minus 5 seconds. The last column displays the calibrated airspeed in knots as computed by the speed advisory system. These speed advisories, which are based on the current aircraft position, altitude, and wind profile, help the controller correct the unequipped aircraft's time error. The speed advisory is recomputed once per minute, using the current aircraft position up to 30 flying miles from touchdown, as long as the delay remains larger than 20 seconds. This feature gives the arrival controller the freedom to issue the advisory at a convenient time. The aircraft below the dashed line are aircraft which will enter the simulated control region at their respective feeder fixes within the next 5 minutes. The feeder fix start times are given in minutes and seconds. As we speed up the simulation and watch aircraft Lima 2, we see it appear at the feeder fix, move along its route, and then receive its first controller command. Reduce its speed, then receive another controller command. Make its turn, then is handed off to the final controller, who issues speed advisories and headings to Lima 2 to bring it into proper landing sequence. Finally, we see Lima 2 landing and is then offed from the simulation. The ATC simulation is also capable of handling missed approaches as seen in the following sequence. The controller tells Sierra 3 to execute a missed approach and gives him a new heading, altitude, and speed to fly to. Sierra 3 is seen heading for waypoint 20. After approximately 2 minutes, a new schedule will be recomputed, and the controller will issue a Capture Probe CP command for Sierra 3 to capture waypoint 53, at which time Sierra 3 will be merged back into traffic for landing sequence. Piloted simulations, such as the Phase 2 simulator of a 727-200 aircraft located in the Manned Vehicle Systems Research Facility at Ames Research Center, have been integrated with the ATC simulation experiment, as in our most recent experiment conducted in January 1987. A new facility is being built for the next ATC simulation experiment, with major emphasis on the Denver Air Route Traffic Control Center aircraft. A Denver ARTCC demonstration based on the new ATC program is planned for the near future. You have just seen a time-based system used in conjunction with appropriate procedures, computer aids, and information displays that provides an efficient method of controlling a complex mix of arrival air traffic, including both high and low performance aircraft, as well as various percentages of 4D